Okay, this video is about IBM Quantum Challenge for 2022, Lab 1. Before I start, I want to briefly introduce that there are 4 labs in this IBM Quantum Challenge, and ultimately it is about error mitigation and Qiskit Runtime. Our Lab 1 is about introduction to primitive on Qiskit Runtime. If you successfully complete this lab, you can receive Foundation badge to show your achievement to others. There is interesting and exciting story ready for you, so please check and watch the video and start our space journey. First of all, I want to explain about primitive. Primitive in dictionary says it is being the first or earliest of the kind are in existence. In the field of biology, mathematics, and 3D modeling, they are equally saying that the primitive is about basic element that is used as building block for more complex elements. Then you might ask questions. How about the primitive in quantum? First, the goal of the primitive in quantum is to make higher level of primitive using categorization and allow more accessibility to building a program. Also, it is important not to use low machine code level. Qiskit Runtime service looks like this image. When you write your code, your quantum circuits and quantum routines will be packaged and sent to the cloud. Then using primitive program in Qiskit Runtime API, it builds quantum circuits and get the result from quantum hardware. Benefits and goal of using Qiskit Runtime is saving latency and reducing overhead for iterative loops. Of course, ultimately, it has a benefit in efficiency, consistency, and customizability. And most important thing is we can use error mitigation and suppression function conveniently. There are 2 keywords I want to introduce for the quantum runtime. These are the session and options. These are the keywords that you will see a lot during this challenge and you will write yourself. Sessions allow you to open and close the primitive in cloud. Also, it defines a job as a collection of iterative calls to the quantum computer. For an option, it configures the current session and parameter. At the same time, it can control execution environment. Currently, there are 2 Qiskit Runtime primitive, and these are sampler and estimator. Let's start with sampler. Sampler uses user circuit as input and generate the error mitigated readout of quasi probability. This error mitigation method and efficient evaluation of the possibility of multiple relevant data points allow better evaluation of short result. First algorithm that used in this lab is Bernstein-Vazirani algorithm. This algorithm is one of the algorithms that shows it has advantage in quantum computer for more complex problems, and it finds the hidden string S. This function returns the bitwise product of the input with hidden string of bit. In classical computer, the function is called number of lengths of hidden string times to get the solution. On the other hand, a quantum computer can solve it with single call with 100% confidence. There are steps to follow for running quantum Bernstein-Vazirani algorithms. First, you need to make n number of qubits with 0 state and 1 output qubit with minus state. Then add Hadamard gate in input register. Then carry the oracle like 001. Again, add the Hadamard gate on the input register qubits. Finally, add the measurement on the input qubits. Now here is exercise 1. You have to build a function that builds Bernstein-Vazirani. So if you input 111 in this function, this corresponding circuit is formed. And when you set your input as 000, this circuit is formed. Now we can make the Vazirani-Bernstein circuit and use 000 and 111 circuit that are introduced earlier to run on Qiskit Runtime. We set the backend as IBM Q Quantum Simulator and in option, set the seed and resilience level. Here the resilience level is 0, so no error mitigation is set. Now we send the circuit using the session, and in this example we are using sampler as primitive. In the first line you set the service and backend, then set the option for sampler. For defining job, use run method with the circuit that you want to run. When you call the output using result, this data come out. But if you want to see the result that we like, we will use result.quasidist. Now we can use what are the outputs and what are the probability for each result for each circuit. When we see here, we can see that result is 7 with probability of 1.0. As we expected, we get 0 with probability of 1.0 from 000 circuit. Next, it is about the parameterized circuit. Primitive simplify the binding multiple parameters in the parameterized circuits. As example, we will use P-gate to build this circuit in the image. Then we will provide 50 data from 0 to 2 pi for the theta. As we can see the result from the circuit, as P-gate is executed, the block sphere shows different rotations with different theta. Now we can execute this circuit with P-gate as our second exercise. As we saw example running the sampler, we can define the sampler, job, and result. For reference, we can set the circuit and parameter values as parameter for run method. The circuit can be defined with one or more circuit, and parameter values is defined the parameters that you want to bind. As you can see this plot, the result from simulation is very similar with the result from the theory. As next primitive, there is the estimator. This is different with sampler. The estimator efficiently calculates and interprets expectation value of quantum operators required for algorithm. This is a program interface that takes circuits and observable. This allows users to selectively group between circuits and observables for execution to efficiently evaluate expectation values and variances for a given parameter input. As one of the important points for the estimator, there should be no measurement in the circuit. We will run P-gate parameterized circuit again, but in estimator this time. First, we will use sparse Pauli op to calculate expectation value of ZZ. Then use this calculated expectation value as parameter observables for a run method in the session. Of course, our estimator result shows similar result as theory value. Hamiltonian is quantum mechanical operator and it has a total energy information including kinetic and potential energy. Since we need parameterized circuit for calculating Hamiltonian, we build the circuit using real amplitude. As our exercise 3, we have to calculate Hamiltonian using 5-qubit circuit in estimator. First, we have to define the circuits for each side using the real amplitude, then define the Hamiltonian expectation value using the sparse Pauli op. Parameters for each circuit, these sets are defined as list from 0 to 1 using numpy linspace. And finally, using this prepared expectation value and other values, we put them all into the estimator and get the result after running it. This is our next big chapter, error mitigation. Unlike error correction that require lots of resource to completely eliminate the error mitigation reduces the effect of the error. Also, the error correction method is not practical for current NISQ due to lots of limitations. In sampler, there are dynamic decoupling and matrix-free measurement mitigation as error mitigation methods, and these are called DD and M3. DD is set as default in Qiskit Runtime and it increases the lifetime of quantum information. If the state of qubit is idle, the leakage of information occurs to the surrounding due to the decoherence. However, DD uses decoupling method to disconnect efficiently from the environment to prevent this leakage. Next, we can use M3 from the sampler by setting the resilience level 1 in option, and this method allows error mitigation for measurement error. M3 works in a reduced subspace defined by the noisy input bit strings, and it allows easier solution of linear system of equation. And when we see the code, we set the resilience level 1 in the option and use it on the sampler for M3 error mitigation method. And when we see the result, the error mitigated result is closer to the theoretical value than noisy simulated result. And these are the error mitigation technique that can be used in estimator. First, this is toward readout error extinction, and there is zero noise extrapolation method. And they are all called T-Rex and digital ZNE for each. T-Rex is default set for the estimator, and it can be also defined setting resilience level 1 in the option for the estimator. And this method uses twirling of gate. The noise is assumed as additional probabilistic gate, and randomly picked noise Pauli gate is conjugated. Therefore, the Pauli gate is added before and after the entangling gate, but making sure the overall unitary is the same, and this method converts the coherent error into the stochastic error. And this stochastic error can be eliminated by sufficient averaging. From this code, we can see that the T-Rex error mitigation is used by setting the resilience level as 1 in the option. Also, the T-Rex error mitigation allows the mitigated result that is very similar to the theoretical value. Lastly, it is about digital ZNE method. Digital ZNE can be activated by setting the resilience level as 2 in option for estimator. And this method do not use any additional quantum resource And a quantum program is altered to run at different levels of processor level. And here we call this is digital since we are not using physical pulse for the mitigation. And this is very active research field for finding out what is the best method to use. Exercise 4 is a multiple choice question, so you can choose which statement is wrong and list them for the submission. Lastly, we are using CHSH inequality. Since the amount of content itself is quite heavy, I cannot cover whole thing here. However, I really recommend to refer to our good resource Qiskit textbook for more detail. We will straightly go to our next exercise. In this section, we have to use error mitigation method to run the circuit to find out what is the hidden message. First, you have to define sampler circuit to run the Bernstein-Vazirani circuit with 1111 in the sampler. Then define the S1 circuit that violates the CHSH inequality for running on Estimator. Next, you can define the expectation values for observables in Estimator. And you can get the result from the sampler and Estimator by these two codes. Now you can see the result of error mitigated CHSH is also very close to simulated value and far from noisy simulated value. For our very last exercise, you can find out what is the hidden message that you get from error mitigation. And after this submission, this is the end of lab 1.